Today is 30 June 2022. This is actually a continuation, or you can see this is the explanation of the Minecraft video I have uploaded in this channel about logic gates, adders, and like 4-bit binary adder I have made. Actually, this was all 1 year ago, as mentioned in that video. Uh, I would try to upload the world if I could, but I don't know how to do that, so I'm not sure about it. I'll pin the Minecraft video below in the comment section. And okay, let's move on to and also I made this when I first started this degree, so about a year ago, as I mentioned. And I actually made this presentation to like educate my friends about what I actually made in that Minecraft world. So yeah, I'm going to explain to you people from that as well. Okay, so these are the basic logic gates: OR gate, NOR gate, AND gate, and AND, and XOR also not. We don't really need XOR in the buffer. Uh, so here you can see that the NOT gate has like a dot in front of it, and this dot is applied for like here we have OR, NOR, and NAND. So basically the OR, NOR is an OR gate with that dot in front. So NOT is the one like that is like the original like dotted one. So this means like basically NOR is OR gate and a NOT gate added together. So at the output there's a NOT gate in front of it. So AND gate is as after the output there's a NOT gate in front of it. So we make it into a simple uh, like make it simpler by making it one complete gate. So that's why there's no AND. And XOR is a different story. We'll get to that. Okay, so these are the truth tables. So truth tables is basically we are tabulating how these, like let's say the top, there are two inputs in each of these gates here, and the let's say the top one as A, bottom one as B. So there is either ones or zeros when we are talking about digital like logic. So okay, here let's see the first AND gate. So we have 0 0. So AND gate is basically does it multiplies the two inputs and outputs the answer. So we have 0 0. So multiplication is 0 0 1 still 0 1 0 still 0 1 1 it is 1. So that's basically AND gate. OR gate is the addition. So 0 0 addition is 0, but 0 1 is 1. 1 0 is 1. 1 1 is still 1 because this is binary, so there's only ones or zeros. We don't really have two in binary. That's why it's still one. Uh, so this is for like gates. This only applies for like gates, but when we actually add binary numbers, we can uh, like let's say when we add uh, 9 and 2 together. So let's take a 9 and 1. Okay, so 9 and 1 together, we can't actually write 10 in one section, so we put 0 and move the 1 to the other area when we're adding numbers. So uh, that's what basically happens when you're adding wider numbers. We talk about that later, but here when it is like a 1 1. So this is a high level addition, so the output should be high in these gates. 0 is taken as low, 1 is as high. Okay, when we move to XOR, so this is an OR gate, but there's a twist. So basically an XOR like it operates for like even in even like low high uh, values at the input. The output is 0, and for odd the output is 1. Also you can check from here that like it is basically like an OR gate, but at the so at the output like output of the 1 1. So OR gate is 1 usually, but an XOR is 0. The other everything like other things are all similar. So have when we have full highs to the inputs, output becomes C. Or else it's just a normal addition that you're doing. Okay. Now we have an AND gate. So this is basically like an AND gate with a not in front. So what a not gate actually does is it inverts. So when if we have give a 0 to the input, the output becomes 1. If we give 1 to the input, the output becomes 0. So this is basically an AND gate with a not gate in front. So we just have to invert the outputs we got from the previous uh, like truth table of the AND gate. So if you see, look at it, yeah, 0 has become 1, 0 still 1, the 0 still 1, and the 1 has become 0. So this is basically the same case for NOR gate. So XNOR is still the same, but we do actually need XNOR for the things we're going to discuss later. But yeah, simple like that. Okay, now before we get into like binary addition, we first need to know about like decimal addition, decimal like numbers in whole first. So here, so yeah, funny number, but yeah, for 2069 and for 2, let's take it as so just for my friends I made this, but yeah, you get the picture. So for 2069 and here, so each of these like has uh, like like from the placement from right to left, each of these numbers has a value. So 9 is in the 10 to the 0 power place, 6 is in the 10 to the 1, 0 is in 10 to the 2, 2 is in the 10 to the 3, and 4 is in 10 to the 4. And this will go on. And because there's a 9 in this place, that placement value is multiplied by 9, and we get it as 9 as shown. And for 6, it multiplies placement value, and it is 60. So yeah, if we just take 69 number, so that means it is a 60 plus 9, so 69. That's how it comes comes into that number. Yeah, so if we take this for 2069, yeah, everything is like then multiplied by the number it shows uh, with the placement value. So when these all add up together, it is clear that we get the same number. Sure. Okay. Now, if we take a binary, it is the same thing, but binary only has one, like binary can't go up to 9 like before. Like here, 9 is, we can put 9, but the binary there's only, we can go up only 1, go up to only 1. So 0 and 1 only. So when there's a 1 in the placement, it basically means that that placement value is directly got. But when there's 0, that placement value is not taken. So here, so at the so first one is the 0th one, the 0 place, first place, second place, it is 4. So it multiplies by 10 for each placement. Sorry, 2 for each placement. Here, the decimal, you can see it multiplies by 10. So here it multiplies by 2. So we say this is a base 10 number, decimal number. It's a binary number because its base is 2. Multiplies by 2 for each placement. As you can see, as the decimal one, this also adds up to I. Now, because we are like taking the decimal equivalents of these placements, the addition is shown in a decimal. So basically, this is showing like if we convert the binary number shown to a decimal number, that's basically what we get, 37. So if we take this 37 and convert it to binary, what we'll get is 100101. Yeah, you can see that's why I have put this table also on the left side. So decimal 0 is represented as this, and it says this. So you can easily get this by thinking like breaking it down as in the right. So for the first one, the placement of 2 the 0 is 1. So yeah, we just need that one for decimal one. 001 is the equivalent to so, as you can picture. Now, so we know the like the placements and like how like know the how these placements and the values like the numbers systems like work. So when we take one of these numbers and adds it to another of the same base, we can only add numbers with the same base. If they are not the same base, we have to convert it to a common base first. Uh, okay, so here on the left, we just have a normal decimal addition. So 1 plus 9, we can't put 10 in the placement, so we put the 0 and move the 1. So, or I would like to use carry the 1 to the left side. So the next placement actually. So that 1 is actually represents a 10. So yeah, uh, so that 1 in the second placement or the first placement, if we take the first one as 0 placement. uh, so 1 plus 2 plus 1 plus 4. So we get 40. So the same thing happens with the binary. Here, the first number is a simple one. So 0, 0 addition is 0, 1, 0, 1, 0, 1, 1, 0, 1, 1. Those addition, that addition could be like represented directly without like any carrying or anything. But this is the second one. There is a carry bit. So 0, 0 is 0, 0 placement, first placement 1, 1. So here 1, 1 should be 2, but we can't put 2 there, just like we couldn't put 10 in the decimal number. So we can't put 2, but what we do is so put 0 there, take that 1. So that 1 represents the like 1 represents uh, like 2 times of the placement. Uh, the basically that represents 2 actually. So like 2 yeah, the addition of the like 2 times the number of the like the addition of the previous placement. So yeah, it puts that one to the other placement, and so then we get 1, 0, 0. So 1 plus 0, 0, so 1. Other one is 0 plus 1. Directly you can get as 1. Yeah. And the bottom one is more complex one. So here 0, 0, 0. 1, 1, we get 0. We put 1 to other side. And we have 1, 1, 1. So 1, 1 equals like 1, 0. But we have another one. So the answer would be 1, 1. So we put 1 here. This is like adding like here, let's say the decimal one we had 2 plus 9. So it should be 11, but we keep the 1 here and take the other one to the other side with the decimal number. Right? So the binary is just like that. We keep the other one here and take the higher one to the other the next placement. So 1 plus 1, 1 plus 0 plus 1. So 1 plus 1 is 0, and the 1 is carried. But see, there is no numbers like in that place, so we just get that one. So this is like this has more digits. The final answer has more digits than the two that was added, because this final number can't be represented by that many bits. It needs more. So that's why it's a bigger number. So okay, we know how these are added. Now, how to actually do it using a circuit. So this is where the uh, these adders comes in. So this is a half adder. This can add like the first two numbers without any problem. So first two numbers in that top left binary number, it doesn't like the first two like doesn't have a carry from somewhere else. So we can, if I just adding these two numbers, so uh, the first placement doesn't have a carry. It's impossible to have another carry. So we can use this half adder. Let's take like here AB is like the, so when we take say AB is the uh, like two numbers of one placement. So here rest is zero placement of both those numbers, like we're adding in the top left corner. So A is 1, B is 0 in that. So that's how we add those together. So okay.